Waveguide filters, a 2FH3 project by Group 33.
The history of waveguide filters. In 1897, Lord Rayleigh first proposed the idea of a waveguide for electromagnetic waves. He proposed that a coaxial transmission cable could have the center conductor removed and waves would still propagate down the inside of the remaining cylindrical conductor. He was also the first to realize that there's a critical wavelength known as the cutoff wavelength, above which propagation was not possible. In the year 1932, George Clark Southworth and J.F. Hargreaves first developed the waveguides in circular form. The first analog filter design was created by George Ashley Campbell in 1910, and his design went beyond the simple single resonator. Rather, it was a lumped element design of capacitors and inductors. This design marked the beginning of filter theory. Much development on waveguide filters was carried out during World War II, and this was driven by the needs of radar and electronic countermeasures. Theoretical work after the war included the commensurate line theory, done by Paul Richards. Commensurate lines are networks in which all the elements are the same length, or in some cases, multiples of the same length. In 1965, S.B. Kahn used dielectric resonators to save space. Dielectric resonators that was used in the 1960s, however, had very poor temperature coefficients. And this is why Massey and Purcell in 1972 used the ceramic resonators. The first of these from Massey and Purcell was used by building ceramic resonators from barium tetratitanate. Jaynes and Edson also proposed an evanescent mode of waveguides as an alternative approach to designing smaller waveguide filters, and these designs were created by Craven and Young in 1966. And ever since then, evanescent mode waveguide filters have been successful, especially where waveguide size or weight are important considerations. In 1972, Moll Meyer first described the use of fine line technology, which uses the inside of a hollow metal waveguide filter. And to today, it is the most recent technology that is being used.
The key parameters of waveguide filters. The waveguide filter can be filled with free space, such as a vacuum, air, or some dielectric with the permeability given by mu and the permittivity given by epsilon. As you can see, the cross-section of a waveguide with long dimensions A and short dimension B, where A is in the x direction and B is in the y direction, with A being greater than B. The z-axis is the direction in which the waveguide is to carry the signal. The fields within the waveguide always have a specific form or wave shape to them called modes. TE, or transverse electric, indicates that the electric field is orthogonal to the axis of the waveguide, so that Ez equals 0. TM, or transverse magnetic, indicates that the magnetic field is orthogonal to the axis of the waveguide, so Hz equals 0. The modes are further classified as TEMN or TMMN, where the M and N indicate the number of wave oscillations for a particular field direction, in the long direction or short direction, respectively. Metal waveguides cannot support the TEM or the transverse electric and magnetic mode because the waves cannot propagate in a waveguide when both Hz and Ez are equal to 0. The cutoff frequency, which is probably the most important parameter, depends on the shape and size of the cross-section of the waveguide, which can be rectangular or circular. The larger the waveguide is, the lower the cutoff frequency for the waveguide is. The formula for the cutoff frequency of a rectangular cross-sectioned waveguide is given by c, the speed of light within the waveguide, divided by 2 times the length of A. Note that the cutoff frequency is independent of the short length B of the waveguide. The cutoff frequency for a waveguide with a circular cross-section of radius A is given by c, the speed of light within the waveguide, divided by 2 pi times the radius of A. The waveguide operating band is the accepted limits of operation. For rectangular waveguides, it is approximately between 125% and 189% of the cutoff frequency. For example, if the cutoff is 6.56 GHz, then the accepted band of operation is 8.2 to 12.4 GHz. Remember, at the lower cutoff, the guide simply stops working. The guide wavelength is the wavelength measured longitudinally down the waveguide depending on the mode of transmission. It's always longer than the wavelength of an electromagnetic wave of the same frequency in free space. The guide wavelength is related to the cutoff frequency, Fc, where lambda is the wavelength the wave would have if unrestricted by the guide. For guides that are filled only with air, this will be the same as the free space wavelength for the transmitted frequency, which is noted as F. Group velocity in a waveguide is the speed at which electromagnetic energy travels in the guide. At lower cutoffs, which is below 6.56 GHz, the wave is slowed to 0, and at higher cutoffs, the wave is about 90% the speed of light. Group delay is defined as the rate of change of transmission phase angle with respect to frequency. Near the lower cutoff, the group delay gets longer and longer as the electromagnetic wave ping-pongs down the guide and can easily be 10 times the free space group delay. But at the upper end of the waveguide's band, the group delay approaches the free space group delay. Characteristic impedance of a waveguide for a particular mode is defined as the ratio of the transverse electric field to the transverse magnetic field of a wave traveling in one direction down the guide. The characteristic impedance for an air-filled waveguide is given by the formula here, where ZF is the impedance of free space, which is approximately 377 ohms. Lambda G is the guide wavelength, and lambda is the wavelength when unrestricted by the guide. For a dielectric filled waveguide, the expression must be divided by the square root of K, where K is the dielectric constant of the material.
First slide. I'm going to talk about the components of the waveguide filter. One component is a resonator or discontinuity with a lumped circuit equivalent of an inductor, capacitor, or an LC resonant circuit, and the filter type will often be named after this component. The second component is a length of guide, and it acts as an impedance transformer, and I'll explain what that is in a few slides. But it has the impedance transformer has the effect of making alternate instances of the first component appear to be a different impedance. Okay, second slide. The lumped element is basically an RLC circuit, which is composed of discrete components that can act as a resonator when both the capacitor and the inductor are included, which limits the oscillations using a resistor of your choice or a resistor of an inductor as a resistor with smaller or larger windings depending on what resistance you want. And having an RLC circuit in lumped element design allows waveguide filters to be smaller in size because the resistive elements can be used to lower the level of a reflected signal in the load in a very wide frequency range, which has low efficiency for matching networks because they attenuate the reflected and the incident wave, which I will explain in the next slide. So waveguide in circuit theory is described by a transmission line that has a length and a self-impedance. So the impedance is the resistance of the circuit component, which is the waveguide here, and the propagation of the wave. So the transmission line is terminated in some impedance, let's say ZL, and that impedance is different from the characteristic impedance Z0, which results in a wave being reflected from the termination of the transmission line back to the source. So the input to the line, the reflected voltage is added to the incident voltage, and the reflected current subtracts because the wave's traveling in the opposite direction from the incident current. It joins two waveguide sections of different wave impedances, so signal power is preserved. Impedance matching is basically how a reflected wave is created. So The reflected wave is added to the incoming waves, creating a standing wave. So impedance matches is very important in the waveguide filter. And the transformers can be used to improve selectivity of resonant circuits. And impedance transformer circuits present the resonant circuit with a source or load resistance that is much larger than what is actually.
There are many types of waveguide filters for the outstanding number of applications in the real world. Here we have a waffle iron filter, named after its internal structure resembling a waffle iron. It's used mostly in the microwave frequency range. Waffle iron filters are best applied when a wide passband or a wide stop band is required. They're also good for removing signal harmonics. They're used in various areas, such as high-power radar, since in most jurisdictions it's required to strictly limit out-of-band transmissions, since these can cause serious interference with other stations. Satellite communications is another area, since out-of-band components and harmonics in satellite signals can seriously interfere with or even stop communication in another band. Another type of filter is a waveguide stub filter. Their range of use is in the microwave to ultra-high frequencies. Their unique design requires them to be connected only at one end. Because of their reactive properties, they may be considered to be frequency-dependent capacitors and frequency-dependent inductors. A common use for them is in antenna impedance matching circuits, in order to maximize power from a source to a load. They're also used for frequency-selective filters, such as low-pass, high-pass, band-pass, and band-stop. Here we have an interdigital filter. They are used in ultra-high to super-high frequencies and is the most compact filter. It serves as a bandpass filter and is required mostly for refining signals in Ethernet and wireless communication, especially to keep up with new fiber optic technology.
An iris is a thin metal plate across the waveguide, with one or more holes in it. It is found that abrupt changes in a waveguide will give rise to a discontinuity that will create standing waves. However, gradual changes in impedance do not cause this. Irises create a discontinuity by exciting modes that are soon to be gone. Vertical edges are parallel to the electric field and excite TE modes. The stored energy in TE modes is mostly the magnetic field. Horizontal edges are parallel to the H field and excite TM modes. In this case, the stored energy is mostly in the E field. These edges can be represented by an inductor and a capacitor respectively. The usual practice is to use an inductive obstacle to create the cavities. However, capacitive obstacles are more suitable for tuning specific frequencies over a wide range. Since inductive obstacles are designed for one frequency and cannot be tuned to a different frequency without changing the bandwidth. A low-pass filter is a filter that passes only low-frequency signals and reduces the amplitude of frequencies higher than the cutoff. An ideal low-pass filter eliminates all frequencies above the cutoff frequency by implementing a square wave function. An impedance converter is a single input op-amp which creates a negative resistance. Thin-line waveguide filters work by having waves move through a thin line of dielectric material with metallization patterns printed onto the surrounding metal enclosure. It has a typical frequency band of 30 GHz to 110 GHz. The metallized dielectric material are called fins and are placed in different locations based on the purpose of the filter. The types of fin line are unilateral, where the fins are only on one side of the substrate; symmetrical, where the fins are spaced evenly apart; bilateral, which is symmetrically positioned substrates with an intervening air gap between them; asymmetric broadside, coupled dielectric fin line, edge-coupled fin line, and antipodal fin line and insulated fin line.